All right, Wiz. Today we're talking about DeepSeek Week. They did a bunch of drops. Really, it's making an impact on the open source community. And it's something that I think has kind of gone under the radar a little bit that we wanted to cover. In fact, the people who know about inference, about actually optimizing LLMs on specific hardware, they're paying attention to this, aren't they?
Oh yeah. This was for a very small subset of the community. This was a very big week that occurred a few weeks ago. I think it's not the case that everyone's going to be super stoked about this. It's probably not the case that everyone's going to want to pursue work like this, but
Yeah.
it is still incredible. The contributions to the community that were made during that week are obviously amazing, and we're excited to dive in and
Yeah.
learn more about exactly what they were doing.
That's right. And we've sort of been moving towards some of this more hyper optimization. And you and I have been chatting quite a bit about as some of the software and the things that we build as AI engineers become more table stakes to actually just be in the game, we have to say, well, how can we do better? How can we get more optimized? How can we actually really make these things work and be more performant at scale, more cost effective, more efficient, more everything, more good, more better, all the way down the stack, and then make more money for enterprise ultimately in the end. And we're really starting to see a little bit more interest in going down to that level, certainly from our students. And I know certainly for us, we love going down there. We've covered recently Flash Attention, also VLLM. We'll bring some of those threads together into this story, but we really have to kind of go down into the hardware and into the ops, don't we here?
Yeah, I mean, this is the magic insight, right? From I think DeepSeek week, right? That I think people were sleeping on before. Not everyone,
That's
obviously,
right.
like the
That's right.
flash attention peeps and stuff, but a lot of organizations, because it really brought this like hyper optimization for my current hardware setup, right?
That's right.
So really right sizing the optimization to the hardware you have access to, and really squeezing every ounce of power that you can get out of your hardware with leaving nothing on the table, thereabouts.
That's right. That's right. And and just to bring this full circle to like what's happening right now today, like actually there's a conference going on this week and it's about GPUs and hardware. And when things like this happen and people release new GPUs, actually this entire optimization scheme of how do we make inference go burr the fastest on some specific GPU, a lot of the stuff we'll talk about today is directly relevant, isn't it?
Yeah, absolutely. Every time there's a new architecture of GPU released, or there's new APIs exposed, or there's new ways to do old things, that allows us to re-explore the hardware and find out if there's an even better, faster, stronger way to do what we've been doing the whole time. Absolutely true.
That's right. That's right. And so, sort of wrapping this together, we talked about optimization last week. And if we could sort of think about the model itself as sort of a software model, we can also think about the model itself sitting on a model itself of hardware. And we're now sort of meta optimizing the whole system. And that's sort of the goal of today, is to get some sort of intuition about how all of that really needs to happen in production. Right.
That's right.
That's
And
right.
it's the classic problem of optimize A, and then you find out that B is the bottleneck. Optimize B, and you can see where this is going.
That's right. And then you got to follow the rabbit trails wherever they lead. All right, let's start following them today. Wiz, we've got some great discussions, and you're going to actually show us behind the scenes of one of the leading frameworks and how they've actually started implementing some of the work that DeepSeek released for free. Excellent. Let's get into it today. We're talking DeepSeek Week today. They really dropped kind of 5++ repos, making a big impact on the industry. If you guys have questions, want to jump into the discussion today, we prefer that you use the Slido link and upvote your favorite questions. We'll make sure we get to them at the end, but also feel free to just smash the chat if we're in the middle of a discussion and you're looking for some additional clarification. We're going to cover a very wide range of hardware and software topics today. Some of you may need a little bit more information as we dig in, and this is a learning experience for me as well. I'm quite interested in digging down into the hardware. We're going to see what we can learn together. Let's get into it today. DeepSeek week, making a big impact. What we want to get out of today is we really want to kind of understand why, one of the leading frameworks today, VLLM, virtual LLM, really open source pioneers, really crushing it, building one of the leading inference systems in production. They saw these releases and they said, this right here, everyone, this is the North Star for LLM inference, and we will get there. So instantly upon an open sourcing of something like this, you see folks in the industry picking it up. This is the through line we really want to stay focused on today. We want to understand how DeepSeek, at least at a high level, decreased cost of actually hosting their APIs, whether it's R1, their reasoning model, or V3, their sort of typical GPT style model. They really optimized how to serve these things up so that, it can be done very cheaply, it can be done very fast, and they can also make plenty of money on it. So this is really, really cool. And this is sort of the leading chart. A ton of releases: FlashMLA, Deep EP, Deep Gem, Dual Pipe, EPLB, Profile Data, 3FS. What do all these letters mean? We're going to figure out by the end of the day. And we really want to kind of really focus on that through line of discussing the future of optimizing the perf of LLMs from the stack all the way up to the level that we're actually building software applications at. So I want to zoom in and I want to sort of contextualize this whole thing by really digging out on this North Star of inference. They released sort of an inference overview system, and it's quite interesting to trace the threads of things we've already looked at on this channel, Flash Attention, VLLM, into today, and where leading companies like DeepSeek are actually optimizing to try to get the most out of their serving and inference. We'll look at each of the releases, we'll discuss them, and then we'll actually look behind VLLM. They said, we'll get there. Let's see how far away they are after just a few weeks of work. So this North Star for inference, this literally comes from VLLM. This is an X post they made. Amazing system. It is now the North Star for LLM inference. We will get there quickly. This was after DeepSeek did their 5 days of releases, and on day 6, they released the inference overview. And there's one chart that was in this inference overview repo that's really kind of the big chart. And you don't have to understand much about this chart to understand that we see income and we see USD here, and we see that the yellow bar cost is quite low, and the blue bar theoretical income is quite high. And this is really cool. This is something, obviously, that if you're an LLM provider is sort of the golden goose. You want to make sure you're keeping costs as low as possible, delivering a great product at scale, delivering it at a cost that's super reasonable for the user, and also being hugely profitable. So the sort of theoretical cost profit margin is in this 545% range. People are talking online, wait, is OpenAI ripping me off? Hey, what's up with the cost structure of all these other companies? If we can really do things like this, why is it that this is so expensive for us today? So really some interesting discussions going on as a result of all of this. And, again, open source is kind of leading the way, just as it always has. So very, very cool to see this. We'll try to sort of break down how they're getting these yellow bars so low. That's sort of the goal of today. And we'll see kind of each step of optimization that they're doing. In order to understand and contextualize this, though, let's remind ourselves what VLLM is. VLLM is a high throughput, memory efficient inference and serving system designed for LLMs. This is from the recent event we did on this right after they had joined kind of the open source PyTorch ecosystem and tripled down on open sourcing last December. They go on to say, and they've done a ton of work, obviously, over the last couple of years, that while they were originally built around their sort of paged attention algorithm, kind of smartly doing attention calculations, VLM has now grown into more of a comprehensive state-of-the-art inference engine. The thriving community has also continuously adding new features and optimizations, including pipeline parallelism, chunked prefill, speculative decoding, disaggregated serving, and more. All of these things, again, they add up to faster inference at scale and hopefully also higher throughput. VLM, kind of born out of paged attention, really, we want to follow the thread back to when they started because it kind of helps to follow the thread for the whole industry. There's sort of a nice indicator here. This idea that actually serving LLMs is challenging and can be surprisingly slow. This is from their blog in June 2023. And the team at VLM had identified that they're slow because the performance is bottlenecked by memory. So, it's been sort of an industry known fact that the bottleneck is memory. The bottleneck of dealing with trying to speed up LLM inference or training. We're talking about compute. We have enough memory, not quite fast enough. And so VLM said, okay, to try to solve this problem, we're going to use this paged attention algorithm. We're going to effectively manage our attention keys and values. This is the idea of a KV cache. And moreover, this KV cache is incredibly useful when you're dealing with an LLM that is going to use some sort of advanced decoding algorithm. That is, I'm going to use parallel sampling. I'm going to use beam search. I'm effectively going to generate multiple output requests per input scenario. And so in that case, a ton of the keys and values are shared across each and every inference. And so if we kind of remind ourselves of the fundamental principle that cache is king, that we want to save cache, we can very easily by caching things that we're going to use over and over again. This was sort of one of the big breakthroughs at the time. And they sort of piggybacked on this idea of virtual memory, which is a quite old idea, where you're effectively turning RAM into these sort of lookup table pages that are swapped in and out. And they did something very similar with LLM, K and V cache blocks, and sort of leveraged this similar idea of virtual memory. So you can see sort of Alan Turing is a can sort of be taken to one block, and that can be used as sort of the initial part of the sequence. Alan Turing is a computer scientist. Alan Turing is a renowned, et cetera, et cetera. And so, you can learn more about VLM in our VLM event that we did recently, but this is important context because they identified this, they built the KV cache, they've been doing micro optimizations ever since. This was also on the back of other people noticing attention was a real issue, especially this K and V and managing your queries, keys, and values. Many papers for many years have been saying, hey, transformers are slow and memory hungry, especially on long sequences, since the time and memory complexity of self-attention are quadratic in sequence length. This is something you'll read all the time. So this complexity, this memory complexity is really important, and it really does slow things down. So the idea of like flash attention was to say, what we're missing here is we're missing attention algorithms that are sort of aware of input output and sort of able to look more closely at them, kind of in this same way of this KV cache idea being implemented as one solution for this. So we want to be able to account between reads and writes of levels of memory, because shuffling memory around is annoying. And this is where we have to start zooming in on GPUs themselves. So, just to be super clear about what we're talking about here, we need to kind of root ourselves in the hardware a bit.
Perhaps some of the most important components, aside from the GPU, are the 24 gigabytes of graphics memory chips, which are technically called GDDR6X.
So what we're talking about is we're talking about that sort of on-chip DDR style GPU memory. And it's really important to distinguish between on-chip memory or on-chip SRAM here versus high bandwidth memory or HBM. And flash attention basically came in 2022 and said, we're going to use this tiling technique to reduce the number of reads and writes between high bandwidth memory and on-chip memory. And the way to think about this is sort of like high bandwidth memory is to a hard drive as GPU on-chip memory is to like RAM. So every time you have to sort of load something from the hard drive into RAM, that takes some time. That's going to be less fast than if it was already on RAM itself. So, the hard drive, you're going to get this slower sort of ability to read and write. It's not directly attached. You're getting this 1.5 to 2 terabytes a second. Whereas if you have this on chip, you can get this very, very quick read write. This is for the A series GPUs from NVIDIA. This is directly attached. And of course, as we come out with newer and newer GPUs, these will fundamentally go up, but the sort of order of magnitude difference between them will not. And so to sort of visualize this, we can kind of think about just literally a hard drive attached to a sort of a GPU.
Environment from the solid state drive into these graphics memory chips.
So this idea that we're going to be able to like just move stuff from the SSD into the graphic memory chip, it's like, yeah, but how and exactly how can we do that in an optimized way to minimize latency, maximize throughput? These are the questions, because GPU architectures, remember, were never created with attention calculations in mind. They were created for graphics processing, right? And so on GPUs, when we're using them for AI and for machine learning, the memory access is always going to be slower than the computation. And this is where, the sort of, okay, well, how do we deal with this? Memory is the bottleneck. Let's do some virtual memory. Let's try to remove this idea that memory is the bottleneck by kind of turning that on chip RAM into more of a paged approach, right? Paged attention. That's where VLLM comes in, the sort of pages idea. And so this way we can sort of, instead of having to do the, exact classic read writes, we can actually speed things up a little bit. Okay, so this went further though, because flash attention and the authors there, they pay attention to this kind of stuff. That was from 2022. If we zoom in on this idea of memory though, what happens? Well, we can start getting into more of the micro optimizations. This is where flash attention 2, flash attention 3 come in. Flash attention 2, what do they say? They say, hey, actually, if we zoom in close enough, it's not just between the on-chip memory and the HBM, there's actually inefficiency due to suboptimal work partitioning between different thread blocks and warps on the GPU, causing either low occupancy or unnecessary shared memory rewrites. And this is where we have to learn a little bit more about, well, what do you mean thread blocks and warps? This is where we have to learn a little bit more about GPU architecture. So let's consider what the GPU chip looks like inside of like an NVIDIA sort of 3090, 3080. What does it look like exactly? Well, let's zoom in.
When we open it up, we find a large chip or die named GA102, built from 28.3 billion transistors. The majority of the area of the chip is taken up by the processing cores, which have a hierarchical organization. Specifically, The chip is divided into 7 graphics processing clusters, or GPCs, and within each processing cluster are 12 streaming multiprocessors, or SMs. Next, inside each of these streaming multiprocessors are 4 warps and 1 ray tracing core, and then inside each warp are 32 CUDA, or shading cores, and 1 tensor core. Across the entire GPU are 10,752 CUDA cores, 336 tensor cores, and 84 ray tracing cores.
Easy, right? Super easy. All right, you guys catch all that? You've probably heard of the idea of a CUDA core, but you have to zoom in quite deeply to get to CUDA cores. And you can see we're sort of optimizing in a flash attention 2 thing, right? At that sort of warp level, which is sort of above the CUDA level. So when we think about these, CUDA cores are sort of simple binary calculators. We can do addition, we can do multiplication, and we can do a few other things. Tensor cores, and for those of you into AI and machine learning, you might imagine these are for doing tensor multiplication stuff, matrix multiplication, matrix addition, used an awful lot for working with neural nets and AI. And of course, the ray tracing cores, while they're actually the largest and fewest, they're used to execute ray tracing algorithms, which are not used in LLMs. Okay, so there's like this entire part of the GPU that is for graphics processing that we don't need for AI. Now, also, moreover, interestingly, this exact same chip is used across the NVIDIA 3080, 3090, 3080 Ti, 3090 Ti. The one we just saw, if it works completely, that's the 3090 Ti. Well, what's the difference between these 3080, 3090s, et cetera? Well, what happens is during manufacturing, dust particles, other defects, they actually get into the GPU and they sort of break parts of the circuits. These defects have to then be sort of quarantined, and that region is shut off. So the 3080 actually has 16 damaged and deactivated streaming multiprocessors, while the 3090 Ti is like pristine. Okay, and this is where the cost difference comes from. So if we want to optimize exactly how we're doing inference at a true, hardware software intersection, we need to worry about things like thread blocks and warps. But if we take it even further, check it out. This is from July 2023, FA2. July 2024, FA3, what we see that, well, actually, it's not just thread blocks and warps. We need to think about GPU-specific architectures. So let's think of the Hopper GPUs. These are the H100s, H200s, H800s you may have heard of. We actually need to not just do all the stuff that we had to do before, but now we also need to exploit the asynchrony of tensor cores. We need to, warp specialize. We need to interleave blockwise matrix multiplication and softmax. We need to block quantization and incoherent processing. We need to leverage block quantization and incoherent processing. In this FP8 low precision, we're getting deeper and deeper and deeper. We're zooming in when we get into hardware specific things. And of course, the H100s have sort of become a bit of a standard here. When they were released, they said, hey, there's 5 groundbreaking new innovations and features here. Of course, this past week, we've had GTC, and there's even newer GPUs with even newer features that we can even more hyper optimize towards. And so this idea that like in FA3, the bottleneck was no longer like just memory or like read writes between HBM and SRAM. It was more than that. Let's read from the top of the paper. Attention is the bottleneck, they say. And they said, flash attention elaborated an approach to speed up attention on GPUs through minimizing memory read writes. Dope. However, it was yet to take advantage of new capabilities in recent hardware. even FA2 was only really getting 35% utilization on the H100, meaning you're only using 35% of the capabilities of your big beefy GPU. That's crazy. Let's not do that. Let's use as much as we can. And okay, so what? Right at the end of the day, this is sort of where we need to get to. A lot of preamble to say, well, so what is we need to be doing stuff like this with Hopper GPUs, and this is what DeepSeek is doing. And so DeepSeek has really said, okay, flash attention people, those are kind of like more researchy, more academic. You're sort of not putting all the pieces together. You sort of see these things slowly start to integrate into the community. But they're like, no, we've been doing all this sort of internal R&D on our product at scale and testing it. And here's what we've got. And they sort of said, our full inference system looks like this. And it looks like per H800 node, we can get this kind of input output. We can get this kind of profit margin. And we optimize all of this through cross-node expert parallelism, powered batch scaling, computation, communication overlap, and load balancing. So I want to go into a couple of these things before we have our first discussion of the day. Let's remind ourselves, VLM saw this, and folks who know, they see this and they're like, wow, yeah, okay, we're coming for you. Thank you for open sourcing this. We're going to go ahead and pick this up as well. We're going to steal like artists. The DeepSeek inference system, it's so simple from the very top, just like all things are, at least in theory. They wanted to optimize two things. They wanted higher throughput and lower latency. They wanted the best of both worlds. They wanted it all. Latency is the time taken for a single request. So if we want to minimize latency, we're going to think about using as many cores as possible for a single request. Throughput is the number of requests handled per second. So if we want to maximize throughput, we want to use as many cores as possible to process multiple requests in parallel. All right. So first discussion. Wes, luck to bring you back up for this. Is this really this kind of inference system that they're putting out there? Is this really the new gold standard for the industry? Because H100s are so popular these days. Is this something that like everybody should be looking at? That we're kind of pretty sure if you're building this kind of thing, you're looking at this. I mean.
Yeah, I mean, kind of. So yes, I think most people who are going to be, running these kinds of models are most certainly going to be very interested in this work. Some of it though is less portable to, I would say, like the normal transformer, right? So there's some MOE specific stuff that I think is probably going to be largely unleveraged by the masses running, regular old dense transformer networks. But absolutely, I mean, some of this stuff you can cherry pick at, right? And there are groups of people who are already cherry picking this for you, right, and putting it into your favorite frameworks. So it's just like flash attention, right? It's something that you have in your tool belt that can make things go burr. It is, is it like always to be used in all situations? The answer to that question is no. Is it to be used whenever you can? Almost certainly, yes.
Yeah. And this idea of like optimizing, hey, I want to minimize latency, I want to maximize throughput. Is this sort of like where everybody has to start? I mean, this to me, it seems pretty fundamental. I mean, you want both, right? You want it all. And so like, this is probably where, I mean, if we think about OpenAI, if we think about Anthropic, if we think about the big model providers, they want to do this too. Maybe the details of the way it looks is slightly different depending on their architecture or the GPU stacks they have. But this idea of like maybe the optimization problem is minimize latency, maximize throughput, utilize all GPUs all the time.
Yeah, and like those two things are competing, right? So it's that classic chart where like the lines cross, so
Right.
you have to pick the optimal point for your organization, and based on what your users are going to be most leveraging, right? So if you're an organization that's kind of relying on this like very heavy sequential agentic flow, like latency is going to be a lot more important, uh, especially when you're getting started, than throughput might, right? If you're just hammering, people are just hammering the model, getting responses, like throughput might be more effective. So it is a, there's a right size to the optimization that you have to also consider, which is, which should you optimize for when. I think the folks at DeepSeek tried to get as much as they could of both, but it feels pretty straightforwardly like they knew the model was going to take many, many tokens to achieve a final answer. And so latency becomes very important when what you're doing is you're producing many, many tokens in a row, right?
Yeah,
So
yeah, yeah,
the
and
dream is
yeah.
we can drive both closer to zero forever, but there, at some point, it's a trade-off, right? So
And we can drive both closer to zero, like, whether we're doing a reasoning model or whether we're doing a standard quick answer, more system one model. Like they did this for both V3 and R1. And it's the same system, right?
it's the same model architecture. So the training, the post training is different. So like the response profile is different, but it's the same, same base model.
Yeah.
And sorry, just a very small quibble of something that I just said. We don't want to drive both to zero. Throughput is something we want to maximize, but the idea is we want both to be at their maximum. Right?
Infinite throughput,
Yeah,
zero latency.
that's right.
That's
Yes.
perfect. Yeah. Okay. And then when we think about GPUs in the future, or we think about AI specific chips coming out from companies like this in the future, I mean, presumably we're going to have to kind of do a lot of this all over again, or maybe some of it ports over. Maybe our favorite frameworks like VLLM will sort of set it up for us, so we don't have to worry about. We just choose the architecture from the drop down menu or the single line of code, and then it's like bada bing, bada boom. The right libraries are applied, but fundamentally on the back end, what's happening is there are different optimizations for each and every configuration. If a new one comes out, then all of a sudden there's opportunity space for like an open source community member to go in there and start contributing, to this sort of, that is the edge. That's the new edge each time, let's say.
Well, and that's it. And I mean, so this is just some interesting little tidbit, okay? That I was having a discussion with a colleague yesterday after the conference day wrapped up, and they had mentioned a paper at NeurIPS, which was talking about how someone was at NeurIPS, which was just 4 months ago or whatever, right? Someone was just discovering how to effectively leverage some of the exposed APIs in Ampere GPUs, which is lagged by a full generation now. So it's the
A100s, right? Yeah.
So it's like we're the hardware manufacturers, from the big ones to the less big ones, right? They're leaving stuff in there that we're not even sure how to leverage yet, right? We're still exploring how to make it go burr, right?
Yeah.
And so this does happen whenever we get new GPUs, but it also happens whenever we find novel architecture, whenever we find a new way to do, a layer in the network, or whenever we change the way we think about the problem, right? And so all of these shifts are very like the two systems are so intrinsically linked, right? That any modification is a new space for exploration. So
yeah, and I'm reminded of like the discussion of like the inference and serving engine versus kind of the whole car or something, right? It's like, so I like VWs, right? And so like the 2.0 T engine, for instance, is like an iconic engine in the line of like VW cars. But there's many different cars that are built around it. And like the 2.0 T has had like decades of refinement and micro optimizations. And even today, people are still like modding them out on, their own and sort of making them more performant and more, more capable. And it sort of opens up this kind of tinkerer industry in the wake of the new GPUs as well, as the older ones become cheaper and you can more easily get a bunch of them and start playing with them. And, so it's really interesting sort of, let's call it a maker space that you could kind of like be in over the next, couple years, over the next few decades in AI. This is something that's definitely going to become more and more important. Okay.
Absolutely true. And I mean, it's such a valid point to bring up the fact that like we haven't had garage or basement tinkerers unleashed on this problem en masse.
That's
And
right.
if the previous 6 generations of GPUs or whatever it's been already signaled, then I imagine we'll find some brand new tricks when
That's right.
those folks get the latest gen hardware.
All right. Thanks for your insights, Wiz. Let's dig into the releases now before we take a look at some of the code. So I want to go ahead and walk through their breakdown of their inference system before we just jump into the straight up releases, because we kind of get some more insight this way. From the top, they said, well, to optimize these two objectives of minimize latency, maximize throughput, our solution employs cross-node expert parallelism. Now, this is a super important point, okay? Wiz just mentioned it briefly, but they are using a mixture of experts model, okay? They are not using a classic dense transformer. They're using a sparse mixture of experts approach in those feed-forward layers. So this is really important because what they do is they use expert parallelism that puts different experts on different GPUs. Now, this is so interesting because obviously for a long time, there's been murmurs in the industry. For instance, this is from the State of AI 2023 talking about GPT-4, quote, Sam Altman won't tell you that GPT-4 has only 220 billion parameters and is a 16-way mixture model with 8 sets of weights, from the PyTorch co-founder, open source legend. This was an old meme that you might remember. This is the case that DeepSeek is using mixture of experts. Now, is OpenAI using MOE? Is Anthropic using MOE? We can't be sure, but you can make your own decision about that. This expert parallelism, though, does seem to be something that does drive the optimization fundamentally. They said, okay, in order to scale throughput, we need to scale the batch size. And then in order to sort of minimize latency, we need to distribute experts across GPUs. And that makes sense intuitively. Want to go up, want to go down. This is the sort of simple thing that we must do. However, when we do this, we increase the complexity of the system, right? So we talked about memory complexity earlier. Time and memory complexity is a fundamental problem being called out in flash attention papers, the original ones. Expert parallelism introduces cross-node communication. We have to optimize this by overlapping communication with computation. It involves multiple nodes. Therefore, we require a data parallelism and load balancing between the different nodes. So these are two problems that come up because of the nature of the competing optimization objectives. We address these challenges by 1, leveraging expert parallelism to scale batch size, 2, hiding communication latency behind computation, and 3, performing load balancing. So when we talk about this sort of large scale cross node expert parallelism, this is a great line from one of the repos that says, due to the large number of experts in DeepSeek v3 and R1, where only 8 experts per layer are activated. This is reminiscent of some of the ideas of, if we quantize low enough, then we can still get a great answer. The high sparsity necessitates an extremely large batch size. The high sparsity necessitates an extremely large overall batch size. This ensures a sufficient batch size per expert, enabling higher throughput and lower latency. Large-scale cross-node expert parallelism is essential. Wes, I want to bring you back up to help us with some intuition behind this idea of batch size. And because of the sparse nature of the MOE, we need this very large batch size that's going to really help us to make sure that we're optimizing throughput as well. Can you walk us through a little bit of your intuition behind this?
I like the meme, first off. Second off, so the idea is like, okay, if I have, remember batch size from training, right? Like, we can just train on like a bunch of stuff at once. Why not, right?
Right.
We can do that as well with inference. We can just do inference on a bunch of stuff at once. Why not, right? Like, the model supports this capability. We can just pipe through, our regular old matrices, but instead of one, many, right? Do all these computations at once. So why not blow it up? And then the reason we want to blow it up because of this sparsity is like, let's say I have 4 requests, okay? And each request uses n out of 256 experts, right? Well, with 4 requests, that is 4 batch size of 4, right? I'm going to be using n times 4. Let's say we're being a little hand wavy with the math here, okay? Let's just pretend like it works out cleanly. We're using like n out of 4 of the experts, right? Well, what if we have instead, we do like a batch size of 100? Well, then we have 400 potential experts being used from this single request, and that's the idea, right? So the crux of the matter is we want to saturate.
That's right.
The number of experts being used. So we want to have a batch size high enough that we're saturating that number of experts being used. We want to make sure that we never have idle experts.
That's right.
And organizations want this too, right? Like, you don't want your SMEs just chilling. You want them working. You want them thinking. The load balancing comes in because there's this intuition, or if you don't have the intuition, you should think about it this way. Some experts are going to be more highly leveraged than other experts, right? So maybe 5 or 6 of my experts are going to be like basically used all the time. Right. And so we need to make sure we have more nodes for those experts than we do for the experts that are less often used. Right. And it becomes this very complex, fun dance of like, what's the right batch size to make sure that all of my experts are saturated, but I'm not overwhelming a few experts that we don't want to tire them out or wind up with another bottleneck there, right?
That's right.
The cool part about this is that it allows you to kind of profile the whole system and understand, right, exactly what experts are doing the brunt of the work. So it allows you to have a lot of really interesting insight. The other thing that I think is something as well I was talking about with my colleague yesterday is, you can imagine that the whole data center becomes a model, right? Like like when you're walking through the racks, you're walking through the model. All of the experts live in different, nodes and different racks. I think it's this. It's really like a network, right? That you have, which is dope. It's just cool, right? But the idea is we want to saturate the experts. We don't want any of them being lazy and sitting around.
Right. Yeah. What's the difference between model and data, really, in the end? Yeah. That's right. Yeah. Okay. I love that. Okay. Then let's we're going to keep it moving. We've got one more quick discussion before we check out the code. Excellent. Thank you, Wiz. Okay. So when we think about, we've done that now. If we now say, now that we've done that, it introduces this significant communication overhead, which Wiz just sort of alluded to. This is where we get that computation and communication overlap. This is where we need to actually deal with the fact that we've got these experts that are maybe more highly leveraged, and we've got to do some kind of balancing of the requests. So this idea of employing a dual batch overlap strategy to hide communication costs and improve overall throughput is something that they're doing by actually splitting a batch of requests into 2 micro batches. So, you batch everything together, then you split it up again. It's like, we're sort of doing again, this kind of dance here. And this large scale parallelism, including data parallelism and expert parallelism, introduces a critical challenge. If a single GPU is overloaded by computation or communication, it becomes the bottleneck, slowing down the entire system. So we want to avoid that. How do we avoid that? Well, we have to balance computation and communication across loads, and they have a number of load balancing things that they've released. They have a prefill load balancer, a decode load balancer, and an expert parallel load balancer. Now, I encourage you guys to read more about this. The optimization objectives for each of these from the repo, balance the prefill load balancer, balance core attention computation across GPUs, equalize input token counts per GPU. Decode load balancer, balance KV cache across GPUs, equalize request counts per GPU. Expert parallel load balancer, balance expert computation on each GPU. So you see the sort of balancing that has to happen. It's a delicate balance. And, this is, they've even visualized it here, but all of this leads up to ultimately, again, more cache, more efficiency, the same performance, but at a really, really hyper optimized scale. And since we just talked about load balancing, I just want to go ahead and go directly into showing you guys the releases from the week. There were 5 days of releases. There was day 1, FlashMLA, day 2, Deep EP, day 3, Deep Gem, day 4, different optimized parallelism strategies, and day 5, 3FS. Knowing what we know now, I think we can dig into these quickly and efficiently in a performant way, let's say. FlashMLA is really focused on decoding for HGPUs. This is where the tie between NVIDIA hardware and the way we actually do computing comes together. It needs to run well on specific GPUs. We're using KV caches. We're using that paged attention. We're leveraging the stuff that we see from previous open source repos and releases. We're leveraging all the stuff, and then we're building on it. So this FlashMLA, flash attention on Hopper GPUs. This is really tying the hardware into that kind of flash attention. Deep EP is just, it's deep expert parallelism, the first open source expert parallelism communication library for mixture of experts models, training, and inference. Efficient and optimized all-to-all communication. Really important. Don't forget, V3 and R1 are mixture of experts models, are OpenAI and Anthropic. We'll leave that up to you guys to decide. But essentially, they're going through each step and they're saying, where's the bottleneck? Where's the bottleneck? We need to optimize the next bottleneck. And so when we get to day 3, day 3 is Deep Gem here. Deep Gem, not Deep EP. Deep Gem, this is when they're going, into kind of the tensor cores that we talked about in the GPU. And they're saying, okay, actually the way that we do matrix multiplication, maybe we could do it faster, right? This is like kind of what the guys at Unsloth are doing all the time. This is, the level of optimization that you really need to be focused in on. We have this GPU, this specific part of this GPU. Can we hyper optimize the specific calculations that are happening down in there after we've done the load balancing, after we've got our higher level optimizations done? Turns out, yes, Deep Gem allows us to do that. Again, Deep Gem supporting both dense and MOE matrix multiplications. Very cool. Day 4, they dropped a bunch of stuff. They dropped dual pipe, they dropped the expert parallelism load balancer, and they dropped profile data. We've talked about 2 of these already. The dual pipe is simply a bidirectional pipeline parallelism algorithm for computation communication overlap. So they're sort of showing you all of the cards on, yes, this EP thing. It has a lot of different, pieces that have to be kind of laid out so that it can work very well. these are the components we needed. And we're going to talk about them more in day 6, which was the inference system overview that we've already went through. And then finally, they optimized so much stuff that they got down to some point to say the 3FS, the fire, flyer, file system, a parallel file system that utilizes the full bandwidth of modern SSDs and RDMA networks. So at some point, they said, well, how can we rip stuff off our file system even faster? And there we have it. That's why VLLM said, hey, this is dope. We're going to get there. We're going to get there. And now it's time, guys, to go ahead and look behind VLLM and see if they've got there. So Wiz is going to take a little test drive around what we're seeing in the VLLM framework today and what they've seemed to have picked up from DeepSeek and what we can sort of intuit as potentially even new industry standards for MOE models. With that, I'm sending it over to you, Wiz, to walk us through.
Oh, yeah. Thank you, Greg. Okay, so the basic idea here is straightforward. The VLLM framework, which is a open source inference framework, was like, oh dang, that's fast. I'm going to go ahead and I'm going to try to steal as much of that as I can. So this is them, talking about the release. Just landed FlashMLA and VLLM, and it's already boosting throughput. So you'll notice that this tweet from VLLM was on the 26th, and the release was on the 23rd. So they're cranking, right? They were cranking. They were getting through these as fast as humanly possible. And this is the idea, right? So we're just going to look at the one instance behind the code, but this is the idea. Like, this is the amount of work that it takes to make this happen, right? The actual code changes are not insane. They're not easy. They're not straightforward. They're just work, right? Because basically our friends at DeepSeek released a lot of that work. It's a lot of just copy pasta, right? So we have just this code basically straight from DeepSeek that's going to be leveraged to make that MLA a little bit faster. I'm just scrolling through code to show you, it's not a lot of changes, right? If we look at the actual commit and we see how many lines of code are involved, it's very small, right? We're talking about 733 lines of code total that changed to get up to 15% increased throughput, and that's just from one of the changes. You can see here that we have the actual implementation, right, which is going to be our FlashMLA with KV cache. The idea is it's fast. That's good. They also just recently released a blog. This was actually released on the 19th of March, which you might recognize as today if you're watching the video live. And they talk about how they and some folks at Red Hat really took this and made this possible in VLLM. So not only did they work on it very hard for the duration of the DeepSeek week, but also they continue to work on it very hard, right? So we can see here increasing maximum token capacity from 67K to 650K and allowing for a larger batch processing. You can see that the throughput with the newest version of MLA, right, is significantly higher throughput. Multi-token prediction. This is one of the things that people have been working on for a long time. So this is not totally novel, but the implementation is complete. Parallelism, scaling DeepSeek R1 efficiently. Right, they've taken the work with the that was released through DeepSeek and integrated it, and they're not done. Right, they're going to keep doing this. Now, the part that I want to focus on, because the blog is great. Please read the blog. I'll drop the link in the chat. But the idea is this is all just something you get when you follow the install instructions for VLLM, right? So when you do this part, or when you run it through Docker, you get these incredible, optimizations thanks to the hard work of these teams. So there's always this intuition, right? Do you have to know how to do this kind of stuff, right? Do you have to know how to do this kind of stuff? And the answer is, for so long as we have the incredible folks at places like DeepSeek and VLLM, you're good. You might be, not at the absolute cutting, bleeding edge, but you're going to be pretty close. It's going to be largely implemented for you quickly and excitedly, because we're all trying to do the same thing, which is run these models as fast as humanly possible. So that's a little tour of how VLM has handled at least one of the integrations. Again, it's not very daunting, right? It's not 10,000 lines of code, and most of it's already written. So if you are interested in this, that's the barrier, right? It's not huge. So I'll go ahead and pass back to Greg to close this out and get some questions. But before I do that, I've got to remind you to subscribe and ring the bell notification. We're live every Wednesday, rain or shine. So thank you so much for your time, and pass it back to Greg to get us to some questions.
All right. Thanks, Wiz. I'll go ahead and have you stay up here with me for a little bit. We've got the conclusions on the day. And, it's cool to see that V3 and R1, officially somebody's being public about it. These are MOE models, and hey, that's part of the secret sauce here. Trying to minimize latency, maximize throughput, do it on GPU-specific architectures. With that GPU-specific attention, the expert parallelism, the load balancing, the faster matrix multiplication, even the file optimization, VLLM said, yo, that looks hype, and it turns out it is pretty hype. They're getting after it. So we've got one interesting question in the chat. If you guys really have anything else you'd like, we can cover that. But the question from Anonymous here is, how does VLLM's page attention mechanism that optimizes key value cache memory enhance the inference efficiency of DeepSeek's MOE? Like, is this like a clean overwrite of like page attention, or is there actually sort of like enhancements that have been made from VLLM that now stack with DeepSeek?
Yeah, so there is some interplay whenever you have KV cache. There are a lot of kernels that they're using that are not compatible. The KV cache size was reduced through some of these enhancements, which can likely take advantage of some of this. But at the end of the day, they're both kind of, they're both trying to make the wheels better. And so there's not as much let's say, constructive interference as there is destructive interference. Like one would be faster. That's the one you should use. There are tiny rough edges that you can kind of optimize a little bit around, but as far as I'm aware, page attention is not adding to the value of the MLA that DeepSeek was using.
Okay. All right. Great question. I want to end on this point, Wiz. So, you talk about these rough edges in between, right? Even to understand these rough edges in between, for folks looking to get more into this, right? To get down into the CUDA level, right? To start being like, yo, what are those rough edges? Like, where do you even start, right? Where are the best places for people to start learning about stuff down in CUDA, stuff like Unsloth is doing, stuff like DeepSeek is doing? What are some trailheads for people here, some resources they can start with?
Yeah, so I have some obvious biases in terms of resources that I think would be a great place to get started. I know a company called NVIDIA that does a lot of kind of beginner intro resources on this kind of thing as a good place to get started. However, to not just say one specific company, places like Modal are a good place to get started with their, I can't remember exactly what the asset's called, but it's like the GPU CUDA handbook or something like that.
Oh,
I'll
yeah.
find it and we'll make sure to link it out. But it's by the folks at Modal. It goes through all the terminology. It helps you orient yourself. Incredibly powerful resource from Charles Fry and team. And then as well, CUDA mode Discord. So the CUDA mode Discord is an incredible place. They have lectures from people that have been in the weeds on this stuff for decades, totally for free. They just ping you at everyone. We've got another legend who's going to talk for 2 hours about this extraordinarily small, part of the system. CUDA mode's an amazing resource to use. If you're looking to get started, I would start with CUDA mode, Modal's resource, which I'll find a link for. And then, of course, NVIDIA's got, entries from CUDA, from C++, from Python, from, all kinds of different entry points and expertise levels. Yeah.
Yep. And I mean, there's just a whole wide world of GPU architecture stuff that as we go further into the optimizations, it's going to matter more and more. Does it matter to you? That's something you guys have to decide. We're pretty interested in the intersection of hardware and software, so we'll keep dabbling. We appreciate you guys that joined us today for this exploratory chat. We look forward to doing more of these in the future. Wiz, thanks for your insights today. Enjoy the rest of the conference, my man. All right. And that's a wrap on the DeepSeek Week recap. We have learned a lot today. We will continue to sort of move towards some of these hyper hardware specific optimizations as they become more relevant to the industry. We wanted to share this one with you because we thought this was one of the ones that really did make the cut. If you enjoyed this content, let us know in the comments and the feedback, and let us know what kind of additional things you'd like us to go deeper on in the future. We're working on some more advanced offerings that might allow us to spend a little bit more time down in the weeds of stuff like this. All right. But in the meantime, if you haven't joined our Discord, please do jump in and start building, shipping, and sharing with us today. If you're looking to actually start building, shipping, and sharing best practice applications, then you might want to join us next week, because we have a very opinionated stance on what the best practice RAG stack is for 2025. We believe this is mature, and it's time for people to go ahead and just say, this is probably the best stack to develop some quick prototypes with. How you integrate it into your system is going to be up to you, and a lot up to how your system operates today already. We'll talk more about all those details and moving from prototype to production next week. If you're looking to accelerate your journey into more of the software side of building these apps and becoming an AI engineer, becoming that unicorn AI engineer that gets really, really good at building up quick prototypes that are production grade and sharing them with whether it's corporate executives or potential startup operators, you might want to consider the AI Engineering Bootcamp Cohort 6. It's coming up. We'll be launching April 1st. And there's a number of application rounds you'll need to go to be considered for this one. We're getting more and more popular. And so we've got limited seating, and the application is a little bit more challenging this time. So check that out if you're interested. If not, maybe check out some of the free content that we've recently put out, including LLM Engineering, the Foundations, which will help you get a little bit closer into what's happening down at this flash attention level, why we need KV caching, why we need to think about how some of these computations are happening at sort of a deeper level within the transformer. So wherever you'd like to go, wherever your interests take you, we've got content that we'd love to support your journey with. You can find it all on the Awesome AIM Index. We have really enjoyed this event today. I personally have learned a lot just by trying to put this together. I look forward to learning more down in the weeds and down in the deets. If you guys are going to do anything over this next week, please consider joining us live tomorrow night for Cohort 5's The AI Engineering Bootcamp Demo Day. This is going to be the biggest demo day event we've ever had. We're going to have nearly 30 demo presentations. It's going to be a veritable mini conference. And we are really proud of all the great work that folks in our community have been doing. And we're excited to showcase it live. You You can find the invite on LinkedIn. It'll be in Zoom, and we're really pumped to show you what we've been building, shipping, and sharing. So join us. And if not, then in the meantime, you should keep building, shipping, and sharing. We will most certainly do the same. We'll see you next week for Practical Rag, or maybe tomorrow for Demo Day. Thanks, everybody. Have a great week. We'll see you next time.